Hi. Hi. Well, thank you to the organizers for having me and all of you. I know it's late for some of you, so it's very nice to see you all here. So yeah, I'm gonna tell you a short story about Motskin polyaminos, and this was joint work with Jean-Luc Varil, Sergei Kirgisov, and Jose Luis Ramirez, whom probably are all here among us. So let's get to it. So the main character of this short story, it's are Motzkin words. So Motzkin words are just words of certain length, say n, in such a way that you can construct them recursively. So you can start. You have to start with w1 equals 1, and you can essentially append something to the right of the word, and whatever you append to the right of the word has to follow this condition that whatever you append was is at most one more than the one that was before the last symbol of the string, and you cannot repeat symbols at all. Okay, so for example, if the length is 1, then the only word that you can have is 1 because w1 has to be 1. If you append something to this 1, the only thing that you can append to that 1 is 2, because if you append 1, you will contradict this condition, and that's about it. That's all you can do because you can go up at most 1. Okay, then you can think of it M3 or M4 just in the same way. So perhaps so maybe M3 is 1 to 1 because you can append a 1 to this string, or you can append a 3. You cannot append a 2 again because you will contradict this condition. Okay, so those are Motzkin words. So it's very clear that they are words, but it's not very clear why they're called Motzkin. Okay, so the way I want to tell you why we call them Motzkin, it's that you can construct a Motzkin path out of them. So at the end, this construction gives you the counting, so you can count these Motzkin words with the Motzkin sequence. And so this transformation works as follows. If you feed the function with 1, you get the empty path. You don't do anything. If you have something bigger than 1, then there are two cases. You either have a 1 in the interior of the word, or you have it. So the words have always to start with a 1 to the left, but in the middle there can be or there cannot be ones. If there is a 1, you have to use the third case, and if there is no 1, you use the second case. Here, 1 plus u means because there are no ones there because you take them away, then all these words have symbols greater than 1, and they start with 2. So when you subtract 1 to every symbol of these words, you get a Motzkin word. And so when you do not have a 1, so is the second case. So what you do is you put a forward step for the Motzkin path. And if you do have a 1, what you do is you go up, you put 1 minus the substring in between the two ones, the first one and the second occurrence, and then you put a down step, and then you put the rest of the word. Because the length is always going down, so this is recursion. At the end, you do it until you get the base case, which is w equals 1. And so that's how you construct a path out of this Motzkin word. So if you get these words, for example, see that this word has a 1 in the middle. So there's a second occurrence of 1. So what you do is you take the substring in between the two ones, which is 2, and you subtract 1, so you get 1. And then you put the say suffix of the word after the second occurrence of 1 here, and then you get up and down. Okay? So if you follow that process, you will get this Motzkin path. So that's why they're called Motzkin. Okay. So what we did was we put a little two-dimensional representation to each of these words. So so this representation is essentially you go through the word, and then you append or you stack a bunch of unit squares, uh, like by columns in a line. And so each column has the number that is in the symbol cells. So for example, this 1, 2, 1, 2, 1 means you put one cell here, two cells, one cell, two cells, one cell, and then you put them together in a line. Okay, so that creates a polynomial. And so now that you have a two-dimensional picture, you can ask yourself about certain statistics, certain geometric statistics. So the three geometric statistics that we consider here in this short story were the interior points, the semi-perimeter, and the area. Okay, so the area is just literally the area of so like you count how many squares you put, which is essentially the same as the sum of all of the symbols, if you want. You can consider the semi-perimeter because it's close picture. Then you know that if you traverse the border of this picture, then you have to have gone up the same times you have to go down. So that means, and the same for right and left. So that means that the perimeter is divisible by 2. And so you can divide by 2, and you get this semi-perimeter. And these interior points are the points that do not touch the boundary. So these are the three statistics that we discuss in here. And so what happens with these three statistics is that there is this nice theorem of discrete geometry called Pick's theorem that relates to three quantities. So Pick's theorem says that if you have a polygon, a simple polygon with integer coordinates, then if you add the number of interior points plus the number of points that lie on the boundary over 2 minus 1, you get the area of the polygon. Okay, and so here you can see that, well, the area is just the area of this thing. The interior points are just interior points. And here you can see that the semi-perimeter is the same thing as counting the number of points on the boundary and divided by 2, just because the segments are always, like, say, on the lattice. Okay, so you can tie this up. So if you know two statistics, you get the other one by 3. Okay. So we bundle together the area and the semi-perimeter, and so we construct this generating function having as information, we have the length of the Munchkin word, we have the semi-perimeter of the word being parameterized by P, and the area by Q, and this V tells us the last symbol of the polyomino. Okay, so the last symbol is the amount of squares on the last column to the right that you put in the polyomino. Okay, so if you consider this last symbol, what you can do is you can create a recurrence, and this recurrence looks exactly like this. Notice that if you put at the end a column I, then there are two cases. You either had one column that had less squares to the left or more squares. If you had more squares, you can put essentially whatever column that you want. But if you had it, if it was smaller, then you can just put one more because of the definition of Munchkin's words. And when you consider that, well, you get this recurrence. This recurrence, when you add over all possible b's, you get this functional equation on these 4 variables. So the length, the semi-perimeter, the area, and the last one. Okay? And so if you plug a 1 somewhere, you get one of the statistics. So for example, if you make q equals v equals 1, then the generating function for the number of polyominoes with certain length of certain semi-perimeter is given by this. So for example, here, if I expand this and we look at x to the power of 5, and this monomial tells us there are 6 polyominoes that are labeled by pink, with semi-perimeter equals to 9. Okay. If you do the same thing with the area, then you get that. So here, this is telling you that there are 3 Munchkin polyominoes with area equal to 9. Okay. And the interior points, we do exactly the same thing. We use exactly the same recursion, but you just have to think to count these points that are here, that are the ones, the last that you put. And with that recursion, you also get a functional equation, and plug in 1 at V, you get that count. You get the count of certain Munchkin polyominoes with exactly a certain amount of interior points. Okay. So for example, here you have the polynomial. Here are labeled. So for example, this 2 means that there are 2 Munchkin polyominoes of length 5. This should be at times, of course. There are 2 polyominoes of length 5 with exactly 1 interior point. Okay. Okay. So if you take these generating functions and you differentiate, then all the statistics go down. And if you plug at 1, then they get sum altogether. So what you get is the total area, total semi-perimeter, and total interior points. And so by doing that, we get these 3 formulas for the semi-perimeter, area, and interior points. Okay. And what I want you to notice is that because we had Fick's theorem, these three quantities are tied together in this formula here. Remember that Fick's theorem has a -1 somewhere, so that -1, because I am adding over all possible Motzkin polyominoes, it becomes the number of Motzkin polyominoes, which is the Motzkin number. Okay, evaluated in -1. In all these formulas, there are three quantities. There are three sequences. Say 3 to the power of n, the central trinomial coefficients, which are the central coefficient of the expansion of this polynomial, and the Motzkin numbers. Okay, and so what happens with this is that when we look further into the second formula of the area, when you expand this polynomial completely, it's a palindromic polynomial, and it has some trinomial coefficients. It's palindromic, and it has degree 2n. So I have a picture. So when you expand, you get these polynomials that have degree 2n. So you have an odd number of monomials, and the one in the center is the Tn that appears in the three formulas back there. And they're palindromic. So the information before the center is the same as the information after the center. And what happens is that when you plug x equals 1 to this expansion, you get, of course, 3 to the power of n on the left-hand side. On the right-hand side, you get the central coefficient, the Tn that appeared before, and then you get twice the sum of the coefficients to the left of the central one. Okay, so you can choose either the ones to the left, or the ones to the right. And what happens at the end of the day is that we can refine the formula for the area, and the refinement is given by these numbers T and K. It happens that if you put all the Motzkin polynomials together and you count the area of all of the rows are at certain height, you're getting exactly this T and K. Okay, so this picture means that, so what you do is you put as a label the monomial that has x as the variable, and the exponential is the total height of the polyomino minus the height of the square that you're placing the monomial. So for example, this one has total height 4. So, and this is at height 1, so you put x to the power of 3. This is at height 2, so you put x to the power of 2, x to the power of 1, and x to the power of 0. So when you add all of those labels, you get the expansion of this polynomial. Okay? And so this refinement was pretty cool, actually, to see happen. Okay, and I guess that's all. I just want to say that the first reference is the paper where you can find more of the results. The second one is some context. These words happen to have so when you take out the restriction of them not being equal to not have consecutive symbols, you get something called Catalan words. And then there is this paper that deals with these same statistics, but with Catalan words. And the third one is for probably someone in the audience was thinking, well, you consider the area, you consider the semi-perimeter, and you consider the interior points. So what happens with exterior points that are interesting? Well, because all of the exterior points are taken into account with semi-perimeter, but there are points that are very important in the exterior that are what are the corners of these things. So if you want to see about those exterior corners, you can take a look at the chart. So thank you very much.